I'm very happy to introduce Gérard Besson, whose position is at the CNRS and University of Grenoble. And since you're all no doubt fortified against collapse, he'll give you a little more of that medicine with his own view, with his collaborators, as you can see, on the geometrization theorem of Thurston.
Okay, thank you very much. So the purpose of this lecture is to give a second version of this collapsing theorem that was addressed this morning by Bruce, a different point of view. So the idea was to try to convince ourselves that it is true without going through lots of details and using the theorem available. So let me explain how it goes. There will be some overlaps with Bruce's lecture this morning, and I apologize for that, but I try to draw pictures so that we'll complete what he precisely explained this morning. So this is a picture of three manifolds, as it should be, or as it is now. So there are some hyperbolic pieces, as was mentioned this morning, which are usually bounded by incompressible tori. All these words will be defined in a minute. And in the middle of this picture, I draw some kind of chaos, which is supposed to be the thin part, which ought to be collapsing and ultimately being identified as a graph manifold. So let's start by recalling a few basic notions. So we'll be working with close connected, and every manifold will be orientable for today. And I'll use this notion of irreducibility. So manifold is irreducible if every embedded two sphere bounds an embedded three ball. So a topological ball. I'll use also, so you have seen on the picture incompressibility. So a surface embedded in M is said to be incompressible if its fundamental group injects by the inclusion map. We'll talk about graph manifolds. So the first stage is to define Seifert. I'll do as Bruce did this morning. Seifert for me will be just a circle bundle over a surface. It's a bit cheating because there may be some exceptional fibers. That's why I call it circle bundle over a two orbifold. It can be reconstructed just by looking at circle bundles over a punctured disk. I don't want to give a precise definition. I'm not sure I know it actually. And a graph manifold. So this Seifert manifold, when the surface has a boundary, the three manifold is bounded by tori so that you can glue them together just by gluing the tori by some diffeomorphism. And the resulting manifold is a graph manifold. So in order to have a precise picture in mind, so this is a picture of a graph manifold. So these circles are circles. The cross means that you product with the surface. And so you have a circle times surface, surface times circle, and you can glue the boundary tori just by interchanging meridian and parallels. So there is one thing that I may say at the moment right now, and that will simplify the rest, is that this manifold collapse. So you can see the collapsing somehow by, you can take the surface to be with constant curvature -1, but just by shrinking the circle. So if you shrink the circle, then the surface may develop a long cusp. So this one like this, and this one like this. So shrink the circle, and then the surface will develop a long cusp. And this gives a collapsing of this manifold. The thing that is important for the rest of the lecture is to go look at the local structure when this manifold collapsed. So that was mentioned by Bruce this morning and described very precisely. But I can say it a little bit differently. So if I want to take a point in the three manifold, for example, the point with a couple of points here and here, I could just rescale the metric so that the circle becomes of length 1. If the circle is very small, then this will rescale this surface, will inflate the surface a lot, and the curvature will be close to 0. So a neighborhood of this point here will be given by a disk here, which is very close to be flat, and this circle, which I have rescaled to be of length 1. So a standard neighborhood of this point, maybe I should write it down, would be something like S1 cross D2, the product metric. Very close to, the disk very close to be flat. If you do the same thing in the middle, what you will see, when it's easy to check, you'll see S1 cross S1, which is a torus, cross the transversal direction, which becomes almost an interval here. So T2 cross I. So you can easily convince yourself that there are two situations for local structure. One is S1 cross D2 on these extreme parts, and in the middle, something like a T2 cross interval in the middle. And this will be, this was mentioned this morning by Bruce, and this will be a description of the local structure in a minute. So the Thurston conjecture is that every irreducible three-manifold admits decomposition as shown on the picture, and he proved one part of this result. So this is the theorem that I wrote on the transparency. So the geometrization is true for Haken manifold. I don't want to define Haken manifold, but in this lecture, what I want to retain is that this is true for manifold with compact manifold with non-empty boundary. And we'll try to reduce the question of collapsing to applying this theorem here. So we retain from this that we know the answer for compact manifold with boundary. So another point which was mentioned in Bruce's lecture this morning is the notion of thick and thin part. So this is everywhere thin. So let me recall the definition. You fix some epsilon, it was called W this morning. And the thin part is the set of points where there is a radius such that on the ball of radius rho, so radius is called rho here, such that on the ball of radius rho, the curvature is bounded below by -1 over rho square, and the volume is small compared to rho cube. And as Bruce mentioned this morning, it's better to understand this after rescaling, so we can always rescale the metric so that the radius is equal to 1. And so the point is thin is if after this rescaling on the ball of radius 1, the curvature is bounded below by -1, and the volume of the ball is less than this constant epsilon that one has taken at the very beginning. So if you are familiar with the Chigger-Gromov collapsing theory, that was also mentioned in Bruce's lecture this morning. This is, so we are going to study collapsing with just a lower bound of the curvature instead of a two-sided bound of the curvature. And this was said by Bruce here. So I guess the number rho was called this morning the scale, if I remember well. And the slight difference between his definition and ours is that we restrict this rho to be between 0 and 1 for some technical reasons which are completely irrelevant. Well, next, the thick part is the complementary set, and there will be no thick part in the sequel. And manifold will be said to be epsilon thin if it is thin everywhere with this epsilon. Okay, so I guess all the words that were on the first picture are defined. So as Michael Aitia said, I could stop now. So maybe I'll go a little bit further. I'll say a few words of the Ricci flow. Again, Bruce has done a great job this morning explaining his technique and also introducing the basic notions. And so if we start with close connected and orientable manifold, the Hamilton Ricci flow is given by the equation that everybody knows by now. And well, I don't want to describe it, but maybe one example which is worth giving because it explains rescaling is that if you start with the closed hyperbolic three-manifold, then the metric evolves by homothéty, and the coefficient can be computed, and it's 1 plus 40 times G0. So it's quite natural to rescale by 1 over 40 if one thinks that on the, as was explained by Bruce, on the thin part, the flow should converge to hyperbolic manifold. So we'll take we'll start with one metric G0 and take a sequence of metric produced by Perelman's version of Ricci flow, that is possibly with some surgeries, and that we rescale by 1 over 40. So for sake of simplicity, I'll take a discrete version of time, so a sequence, which I call Gn. And that's the only thing, more or less the only thing I want to retain from the Ricci flow, except that Bruce also mentioned this morning that there is a very nice technical property which he did not write, and I won't write it either because it's a bit technical to write, but Perelman's proof gives also, maybe at a much smaller scale than the one that we have seen before, control on the curvature and its derivative. So you can choose in advance a certain number, and if you work sufficiently, you can get more than a family of metric, but also a control on a small scale, very small scale, but still it's useful of all derivatives of the curvature up to the number that you have chosen at the beginning. So this, as Bruce mentioned this morning, avoids using Alexandrov spaces. I have nothing against Alexandrov spaces, but I mean, it makes it easier in what I want to explain. So when we take limits, so again, Bruce explained this very well. When we take limits, so the convergence is very strong because the flow is regularizing, and so the convergence is in CK topology for K very large. So the manifold which are close together are diffeomorphic and up to a high order, and this control of curvature allows to take a limit in a reasonable sense without bothering about, regularity of the limit. So the result I want to discuss is the following. So let me write the results. So we'll consider a manifold M such that there exists a matrix coming from the flow with these properties, this property that I mentioned before, which becomes epsilon n thin which is epsilon n thin with an epsilon n going to 0. And I want to conclude that this is a graph manifold. So there are some hypotheses. So I assume that M3 is closed, connected and orientable. These are basic stuff. Irreducible. So irreducibility is quite natural in this context. It's armless. Without embedded RP2, well, that's also armless. It's just to avoid some technicalities, some cases, actually. So it's armless because you can check easily that closed, connected, orientable, and irreducible manifold, which has an RP2 embedded, is RP3. It's very easy to check. And hence, RP3 we know, we don't have to understand its topology, so I can get rid of RP2s. And there is one hypothesis which we don't like, but unfortunately we cannot get rid of, is that we have to assume that the manifold is not simply connected. And that I'll explain later where we have this limitation, where this limitation comes from. Okay, good. So the idea of the proof is exactly the one that Bruce described this morning. We have, first of all, to understand local situation. And then we have to try to glue these local models together to understand the global picture. So what Bruce explained, and that's where the two proofs differs, that, they work very hard, and it's a very nice result to understand the graph structure. So we have to glue this local picture and try to produce the graph structure. Here we'll use a shortcut at the price of using other theorems, which I'll describe in a minute. Okay, so the other approach were mentioned this morning. Perelman, Shioya Yamaguchi, Karpovich is the one who wrote the details of Perelman stability theorem for Alexandrov spaces. Morgantian, Sauge, and Kleiner-Lotz. So the order is irrelevant, just the order on which it has been posted on the archive. For example, Kleiner-Lotz result that was mentioned this morning were announced 2 years ago in this room, if I remember well. So, okay, but it takes a while to write the details. So the order is completely irrelevant, just the order in which it has been posted. So by the way, we owe a lot to Bruce's and John Lott notes, which have been posted on the internet on the Ricci flow, without which probably we won't have been able to do anything. So it's my pleasure to thank them for that. Okay, so let's start with the proof. So here I draw a picture of non-compact manifolds and non-negative curvature. So it comes from Chigger-Gromol theory that was already mentioned this morning, that the manifold is like this. What do I mean by like this? There is a compact core, which is called the soul, which is totally geodesic, convex, totally geodesic, and with non-negative curvature, on which the manifold is a bundle. It's a diffeomorphic bundle, and even a submersion that was proved by Perelman. And we'll show, I won't show it today, but it's a classical fact that locally around a collapsing manifold, then the structure looks like a tubular neighborhood of the soul. So this is, so when one is interested in the collapsing with a two-sided bound on the curvature, there is this beautiful theory by Chigger and Gromov, which prove that in that situation, locally there is this structure which glue together to a F structure with positive rank. Here it's a version of that, but which I'm going to describe. So each point in the sequence of manifold collapsing as a neighborhood which is close to a piece of non-negatively curved manifold, in fact close to a tubular neighborhood of the soul. So to be more precise, and I need this precision, I don't like to write so many details, but you fix a number capital D which is going to be very large at the end. And for n large enough, so remember that we are working with a sequence, so there is an index n floating around, large depending on this capital D. Every point in M has, for every point there exists a radius nu x and a non-compact, non-negatively curved manifold such that the ball around x of radius nu x is close to the tubular neighborhood of the soul of this non-compact manifold. And closeness is measured by this number d, and that will be useful at the end. So two other properties that will be useful is that the volume of this ball is small. So it's comparable to, so it's smaller than the radius cube divided by this number d. So if we choose d very large, then this number would be very small. And the curvature, as usual, is at the scale of the ball, which means that the curvature is bounded below by -1 of the radius square, which is always a thing that we can get here. There is one case which I forgot. So it's the case when the whole manifold is close to a non-negatively curved manifold. But this was explained this morning already by Bruce. First of all, this closeness implied that the M will be diffeomorphic to a non-negatively curved closed manifold, compact manifold. And thanks to Hamilton's very first result on the Ricci flow, so these two papers in 82, the seminal paper and the second one in 86, we know the structure of these manifolds. So Bruce explained they are a quotient of S3, S1 cross S2 or R cross S2, and R3 if they are flat. So they are all graph manifold and don't have anything to prove. So let's stick to the first case where only locally we have these structure which are very similar to non-negatively curved manifold. And everywhere, everything depends on n, nu x, x, everything, capital X, everything depends on n. And of course, it's a mess to write it down, so just omit it. When something does not depend on n, I will say it's uniform. Okay, so the picture again. And again, so the proof is done by contradiction, and it's exactly the thing that I described here. You suitably rescale the manifold near the point, for example, by something close to the injectivity radius, and you show that if this is not the case, you have a sequence of manifolds such that if you rescale, then it converges to non-negatively curved non-compact manifold, in which case you get a contradiction. But this, I mean, you can think to this example, which is the proof is done exactly in the same way. There is no mystery here. Very easy to do. Well, okay, so then the classification of the structure is very easy because we have to just to understand the soul, and then it's a bundle in the soul. And the soul has dimensions strictly less than the dimension of the manifold because the manifold is non-compact, the soul is compact. So the possibilities for the soul are very limited. It has to be non-negatively curved, so it's a point, S1, S2, T2, or the Klein bottle. I should have added RP2, but RP2 is excluded from the very beginning. And hence, the metric ball, which is close to the soul, it has to be diffeomorphic to B3, S1 cross D2. This is one example here. S2 cross an interval, or T2 cross an interval. This is another example here. Or the Klein bottle, the interval bundle over the Klein bottle, which is a twisted bundle. It has to be twisted because it has to be orientable. The Klein bottle is not. So we have 5 possibilities for the local structure of these manifolds. And that's now the structure of our proof differs. So now it diverges from what was explained this morning. So Bruce has explained that in their proof they're trying to match very carefully the fibration to get a global picture of the graph manifold. So we'll do a completely different approach, which it's simpler, but it has to use a lot of other theorems. So the approach is very inspired, and more than inspired, by a paper by Gromov, which is volume and bounded cohomology. And let me start to describe it now. So first of all, I changed notation because this nu is very complicated to write. So I use Ri for nu of xi. And so we have these local models with our metric balls, and I will construct a covering, a finite covering by these local models. So first we take a maximal packing by balls of radius 1/4 of the Ri, so that the balls of radius Ri forms a covering of the manifold. Everything depends on n at the moment here. And this covering has a nerve, and which is just a subset of the Q minus 1 dimensional standard simplex, where Q is just the number of balls that has been taken here, which could depend on n. So in case you don't know, I'm pretty sure that everybody knows, but the nerve is just a subset of the standard simplex, the one which is with a sum in Rn plus 1 with the sum of coordinates equal to 1. And there is one point, one vertex for each set, one edge anytime 2, and only 2 of these sets intersect, so one triangle when 3 and only 3 intersects, and so on and so forth. And we'll see how to construct it later. Okay, so one important fact is this has a finite dimension. And so there is an a priori uniform. Uniform means it does not depend on n, on the number of overlaps at each point. So I won't prove it, but the idea is very simple. First of all, if you have a lot of these balls around the point, for example, balls of radius of 1/4 of Ri, you look around this point at the local model. So you have a lot of balls, of small balls included. And if you take the packing version, so these small balls do not intersect, then you can just apply, remember that we have local curvature bounds. So the curvature is bounded below in these balls. So then we can apply the standard comparison theorem, the Bishop-Gromov comparison theorem, which gives a bound on the number of balls that you can pack in a bigger ball. Of course, I mean, the radii are not the same. If you are familiar with this, the use of this comparison theorem, the radii are not the same. But here we can show, and it was also, well, it was in the paper by Gromov, that if two such balls intersect, then the radii are not really different. The ratio is bounded by 4 and bounded below by 1/4. So these balls, when they intersect, they have kind of similar radii, and so you cannot pack a lot in a small area. And that gives really, one has to check this, it's pretty easy, but that gives really a uniform bound on the number of overlaps that you can get. So a bound on the dimension of this nerve here, a uniform, independent on n, and that's very important. So now let me construct, so following Misha's paper, let's construct a map from the manifold to the nerve. So the map is straightforward to construct. You can take cutoff functions on each ball, and you can have them as coordinates for a map into R Q plus 1. And if you wanted to go into the nerve, you have just to divide by the sum, which is not 0. So the standard construction of a map from the manifold into the nerve. So far there is nothing fantastic, but I mean the next thing is very important, is you can do so that the Lipschitz constant of this map is bounded on each ball. So it's bounded by some uniform constant independent of n divided by the radius of the ball. So, but it's still, this is a very nice bound. In order to do that, you really need the a priori bound on the number of overlaps. But when you have, as soon as you have that, it's very easy to construct such, well, to check this by taking a reasonable partition of unity. So we have a map whose Lipschitz, whose dilation is bounded on each ball well, if the radii are small, the bound is very big, but still it's very useful. And the next thing which is useful is that the pullback of the open star, the ith vertex. So the open star, the ith vertex, take a vertex, and the open star is the union of the open simplices which touches this vertex. And so if you remember, a vertex is one ball, an edge is intersection of this ball with something else, a triangle intersection with this ball with two other objects. So the pullback of the open star of some vertex is included in the ball which corresponds to the vertex. Okay, now the game, again following Gromov, is to, so this is a very neat idea. If the volume of the balls are very small, then you can push this map, you can deform this map, homotop it, into a map from the manifold M into the two skeleton. So you can deform it as a map into the two skeleton, relatively to the two skeleton that is fixed, with furthermore this property that the new map as the pullback by the new map of the open star, the if vertex, is again included in the ball, in the metric ball one started with, and that's very important for the rest. So you can deform, so in some sense, if we define open set, the map is continuous, open set as it's written here, VI, so we have shrunk the original covering to a smaller covering, such a way that a new nerve has dimension 2, at most 2. So if you think to having a covering on the manifold and trying to shrink it, if you do it by hand, you shrink one set and then you shrink another one, and then there is a hole and it's a mess. So this is a good way to shrink a covering, but the question is how can we reach the dimension which is smaller than the dimension of the manifold? And this is just a consequence of the estimate on the volume I started with. So let me describe very briefly the proof. So there is a standard step, which is to reduce the map to a map into the skeleton of the same dimension of the manifold. Let me skip this step, which is pretty standard. And let me explain how you go below the dimension of the manifold. So the point is now we have a nerve where there may be three simplices. And the only thing we want to show is that the three simplex, any three simplex is not filled by the map, so that there is a point in the middle which is not reached by the map. And then you can use central projection. And how do you get that? Again, we used Gromov's paper. How do you get that? It's a simple computation, volume computation. So let me read these two lines, which is the only proof that I will be making. So if you look at the volume of the image inside the three simplex, and of course we are inside a simplex, and it's in the open star, well, in the star of any vertex. So certainly this is included in the image of one of the ball corresponding to one vertex. So it's this bound on the volume. Now we can use the fact that the map F is Lipschitz on each ball. And you can combine the estimate on the Lipschitz constant with the estimate on the volume of balls that we got at the very beginning, metric balls. And it's really great because the radius just cancel. And what is left is something like a uniform constant c to the cube divided by this number d, which is our flexibility here. So if we choose from the very beginning d large enough so that this is less than the volume of the standard simplex of dimension 3, then it's clear that we cannot fill it completely. And so this is a straightforward. So the idea is very simple. I mean, if you have covering by balls, and if you know that the nerve is an upper bound, and if you know that the volume of balls are very small, then you can reduce the map that I have constructed, that Gromov has constructed in his paper, to something to something in the two skeleton, in the lower dimensional skeleton. And so in Gromov's paper, this technique is used to prove the so-called isolation theorem for a simplicial volume, which I'll mention maybe later. Okay, then you compose. Then you take one point in each three simplex which is not reached by map F, and you compose by central projection, and you get a retraction. How much time did it maybe? Okay, well, it's almost finished anyway. 20 minutes more than enough. I have to slow down, or maybe I stopped before. Okay, 10. 10 is fine. Okay, great. So this is the only argument now. I have to explain how we apply this twice, and that's finished. So let's come back to the scheme of the proof of the theorem that I mentioned at the beginning. The idea is extremely naive because you have this three manifold covered by these metric balls, and you want to apply Thurston results for manifold with boundary. So just take out one of these balls, and what is left is a manifold with boundary. I know it sounds ridiculous, but it is actually. The only problem is that this manifold with boundary has to be proved to be Haken or to be proved to be irreducible. So that's the key step. We have to show that when you take this ball out, what is left is irreducible. So let's try to do this. Well, let's take so I will call V, so this cal V, the local model that I have taken out. So M minus V is this manifold with boundary. We'll see what's the boundary later. And let's take an embedded two-sphere. So first of all, this embedded two-sphere in the big manifold it does separate here. It separates because in an irreducible manifold, the two-sphere separates, usually. So it's an easy exercise to check. And now in this big manifold, which is irreducible, it bounds a three ball. So we can always isotope the three ball to be on one side on the other. So let's think of this two-sphere bounding a three ball in M, a topological ball. Now it's a topological ball, not a metric ball. If this topological ball is on the side of F minus V, then we are done. I mean, it bounds a topological ball in M minus V. But the problem is when it's on the other side. If it's on the other side, then it has to contain the local model, and we are stuck. Okay, we are stuck, so we can take another local model and try with the other one. So with this proof, we are always stuck when all local models are included in topological ball. And there's nothing we can do. So let's try to prove that there is a local model, which I call V, which is a metric ball with this radius of nu of x that I mentioned at the beginning, which is not included in a topological ball. So a way to do this is to show that it's not homotopically trivial. That is, the image of the fundamental group is not trivial in the manifold. So let's try to do this. Well, it's a proof by contradiction. If it's complete, if all these local models are trivial, we can do the same thing than before. Construct a covering, shrink the covering. The new covering, which I call VI before, all the VIs were included in the balls, in the metric balls, and it's also homotopically trivial. And then we are lucky enough, there is a theorem by these two Mexican mathematicians, Gomez Larrañaga and González Acuña, which says that this is not possible unless a manifold is simply connected. So a theorem stated here, if a closed connected orientable irreducible free manifold has a covering of dimension at most 2, so this is dimension of the nerve, by open subsets which are homotopically trivial, then M has to be simply connected. So that's why we add the hypothesis, not, if the manifold is supposed to be not simply connected, then we are in good shape. So this was suggested to one of us by John Morgan. And so before this, we had a stronger hypothesis in order to have this technique work. We supposed that the manifold was aspherical, or it has infinite fundamental group. And then we used, at the time, a covering theorem due to Macmillan for aspherical manifold. But okay, now this, so it's a pity in some sense because we just missed the Poincaré conjecture, but it can be proved differently. And by the way, since there are very great topologists in the audience, there is a question which I should ask. Maybe it's stupid, but many things are stupid in my lecture. So the question is, can we conclude from this, instead of simply connected, can we conclude that the manifold is a sphere? Of course, without using Poincaré conjecture. Is it as difficult as the Poincaré conjecture? Much easier? I don't know. I have absolutely no idea. If some of you has an idea, I'd be happy to hear the answer. Probably as difficult. But thanks to John Morgan, we can deal with that. So now we are in good shape and almost finished. We have so one of this local model, this ball, which is homotopically non-trivial. So, and in the list of 5, if we look at this list, only 3 are not simply connected, these ones. And one can check that the boundary is a union of, well, it's 1 tori or a union of 2 tori. So the manifold M minus V is a manifold with boundary, which is irreducible. And hence, it has a geometric decomposition. That is, it can be decomposed along incompressible tori into hyperbolic pieces and graph pieces. Well, ultimately, we want to show that the only graphs are there, so we have to exclude hyperbolic pieces. So how can you exclude hyperbolic pieces? Well, again, we come back to the same paper by Gromov, and in this paper, he produced an invariant, numerical invariant, which tells us exactly what to do. And the invariant is a simplicial volume. So if we can show that simplicial volume of this manifold is 0, then we are done. So why is that? Let me explain. So I wrote a definition of the simplicial volume. Let's think the manifold has no boundary. Just write a fundamental class as a sum of simplices with coefficient in R and take the L1 norm as the coefficient and take the infimum of all possibilities. So so this is a number, which is the norm of the manifold, and it's a very powerful invariant. So here's a property in dimension 3. So if a manifold has a geometric decomposition, and if the hyperbolic pieces are denoted HI here, then the simplicial volume can be computed. So here you need to use several things. First of all, Gromov proved that if you glue 2 manifolds along some, let's say on dimension 3 along a torus, then the simplicial volume is additive. In general, if you glue 2 manifolds along, for example, a submanifold whose fundamental group is amenable, then it is additive. Then it's very easy to see that if there is a collapsing, so for example, on graph manifold, then the simplicial volume has to be 0. And it's not too difficult to check that on a finite volume hyperbolic manifold, the simplicial volume is essentially the volume of the manifold up to some constant, which is the V3 here, which is the volume of the maximal ideal simplex in the hyperbolic space. So it's Gromov part with Thurston. Soma did the case where you use annuli. The story is very interesting. And I mean, everything is written in volume and bound cohomology. So, but the corollary is exactly what we wanted. If a manifold has a geometric decomposition, then we can say if it's graph or not just by computing this number. And so again, I mean, how can you show that this number is 0? The same technique works, and we have to rely on also a theorem. So you start with this covering as before. Now you have to cover the manifold with a boundary. So we may have to be careful with the boundary. We may have to shrink a little bit the local model, but that's technical issues which are not very difficult to handle. And you can shrink it to be of dimension at most 2. And maybe you have to be careful with the boundary. It has to be covered by one of these sets, so dimension 0. Well, you look at the list of 3 possibilities that have all fundamental groups are virtually abelian. So in particular, amenable. And then we can use one, again, we come back to Gromov, and where he has a vanishing theorem in his paper. So I just wrote the version that we need. The theorem is much more, I mean, it covers much more case. In fact, you should replace virtually abelian by amenable. So if you have a manifold and a covering, all my coverings are finite dimensional, so the manifold is closed here, or compact. A covering whose dimension is less than the dimension of manifold and such that the fundamental group of the set that you use fundamental group gives in the manifold virtually abelian or amenable group, then the simplicial volume is 0. There is not even enough complexity to force the simplicial volume to be non-zero. And so we are done. Actually, I'm sorry it's finished. So now let me say a few more things. So this technique is completely borrowed from Gromov. So in this paper, completely borrowed from the proof of this isolation theorem. So the isolation theorem tells that if one has a compact manifold, let's say a closed manifold with a Ricci curvature bounded below, and if all balls of radius 1 are a small volume, then the same technique shows that the manifold has to be, the simplicial volume has to be 0. And it's usually, I mean, it's very useful if you use it in the reverse way. If the simplicial volume is not 0 and Ricci curvature is bounded below, then there is a point where the volume of balls of radius 1 is large. So it replaces the injectivity radius. Okay, so this, the conclusion is that well, this is a graph manifold. It's not difficult to see that if you glue back this very special model that you understand, what is left is a graph manifold. So the ideas are borrowed from Gromov, Chigger-Gromov, Chigger-Gromol. And it already appeared in these papers and book. The last one is a book. And Boileau, Leib, Porty, they wrote the proof of geometrization of orbifolds. It was published in the Annals. Don't ask me what I've done in this story. I'm just giving this lecture, more or less. So I want to finish by quoting Etienne Gis' lecture. He said that mathematics is a question of groups. So his group was much larger than ours, his group of 5. And it has been very nice. We have been working on this Ricci flow. I mean, the part which is technical, the analysis part, for so many times. And it ends in the same way than Etienne Gis' group activity by a book, which is about to be published, where we wrote these details about the Ricci flow and details of this approach for the geometrization. So they will be published in the European Mathematical Society. I'm happy to thank the people from the EMS who helped us a lot with the book. Okay, I stop here. Thank you very much.